Welcome to course on wastewater characteristics and the lecture on sampling. In this lecture, I will cover several topics: general principle of sampling, sampling plan and monitoring program, types of samples, numbered volume of samples, sample collection and handling, operation practices and advices, and examples of a full and lab scale sampling campaign. Sampling in general is applied to all kinds of domains, and it's very present in water systems. In different domains of water systems, like water supply, where we talk about resources, transport, treatment and distribution, also in the sewer sanitation, urban drainage and sewerage, wastewater treatment and product disposal and reuse, and non-sewer sanitation, containment, transport, treatment and product disposal and reuse. In this presentation, we will specifically focus on wastewater treatment sampling. And at different scales. We will talk about full-scale sampling, pilot-scale sampling, and laboratory or bench-scale sampling. In this slide, I made an attempt to connect sampling with the wastewater treatment plant life cycle. The wastewater treatment plant life cycle consists of design, construction, operation, and evaluation stages. The design stage starts with the system choice, preliminary design, final and functional design, operator education, wastewater treatment plant startup, optimization, problem solving, and the future prognosis. So sampling is applicable to any of these steps. So let's take a look what kind of sampling we need to consider at different stages of wastewater treatment plant life cycle. When we talk about the system choice, we are speaking mostly about wastewater, and if fecal sludge and septic sludge is involved, then we talk also about this media. And we talk about influent sampling. And the scope of sampling is relatively basic. When we talk about preliminary design, we are still talking about wastewater and fecal sludge and septic sludge, influent sampling, but the scope is, let's say, basic plus. So it's a little bit wider than when we talk about system choice sampling. At this stage, we are really collecting primary, often static data on influent quality and quality, and we call this flow and load report. Static data are average data opposite to dynamic data. When we talk about preliminary design, we still talk about the collection of data which are necessary really for the purpose of preliminary design, and may also include some dynamic data, so some variations in the inflow to the wastewater treatment plant. Then we can talk about final design, where the scope is wastewater, and if we have a fecal and septic sludge intrusion, we talk still about influent sampling, but the scope is now extended. We need more information about wastewater when we want to make a final design. We are collecting data necessary for the purpose of detailed design and functional designs, preferably dynamic data, daily, weekly, and seasonal variations. In the meantime, we also need to educate operators. In that case, we are still focusing on wastewater, but now also on sludge characterization and hands-on training. So the sampling is a part of the hands-on training for plant operators. In this case, samples are collected for the purpose of education of the plant managers and operators. Then the treatment plant is started up. It's a very special stage of the life cycle of the plant. And in this case, we are having also effluent, because plant is now operational and has influent and effluent, but also process units in between. So we are looking into influent and effluent sampling, plus in this stage specifically, we are also looking for performance of individual units, and therefore we have to include them. At this stage, we are acquiring the data that can be used to document plant performance at a given treatment operation or process. We are also collecting routine operating data for overall plant performance, and we also need data to consolidate reports, regulatory compliances, and determining user fees. Once the plant is fully operational, often we are going to optimize operation of such plants. In this case, we cover by sampling usually process units, influent and effluent, and all kind of information we want to collect which are related to the optimization. Sometimes some optimization tests are performed and we collect data from these optimization tests. We also use information from sampling to solve the problems. Often these problems are at the level of units, therefore we need to sample these units, not only in front or after the units, but sometimes also inside the units. And we need to check how this problem solving is influencing our effluent and what is in the influent. So we also need to include that into the scope of sampling. In this case, we acquire data that can be used for troubleshooting. We collect data needed for improvement or fine-tuning of plant operation, sometimes also from research projects and experiments. And at the end of the cycle, we also look about the future and how we use the lessons learned from the existing operations and practices to improve our future investments. In this case, we use sampling to obtain data that can be used to implement new programs for sewerage and or wastewater treatment plants. One should note that model-based design, operation and optimization will likely increase both size and scope of the sampling program. Why is that? Because model normally includes more parameters than regular design procedures which are not model-based. By using the models, you also need to feed the models with the data, and to obtain this data, often additional sampling is needed, with the scope which is larger than the scope when you don't use the models. But later on, in the modeling course, you will see how many advantages are of using the models, and you will also understand why we are so willing to expand the sampling schemes and data acquisition to feed the models, because the use of the models is beneficiary for many reasons. To know more about that, please refer to the course on modeling, which is part of this biological wastewater treatment plant series. Let's talk about general objective of sampling. The objective of sampling is to obtain a portion of material small enough in volume to be collected and transported conveniently and yet large enough for analytical purpose while still accurately representing the material being sampled, so it will not deteriorate or become contaminated or compromised before it is analyzed. This objective implies that the relative proportions or concentrations of all pertinent components will be the same in the samples as in the material being sampled, and that the sample will be handled in such a way that no significant changes in composition occur before the tests are made. Now we come to the most interesting part, and these are sampling questions. These are the questions that one should always ask himself or herself before you start sampling. The first question is why? The question why is about the purpose, objectives and aims of sampling. Without that, you cannot start sampling. You need to know why do you do that. It's a trivial question, but it's a very important question to answer at the beginning of your sampling program. After that, there are 4 questions that I here highlight in blue, and these are what, where, when and how often. What to sample is actually to make a decision which parameters in wastewater you want to sample. This is very important because wastewater characterization has a long list of parameters, and you need to decide which parameters are of interest to your study, and that is also linked to the purpose of sampling. So once you know what you want, why you want to sample, then you also have to make decisions on parameters that you want to sample. After you make these decisions, then the next answer you have to do is where to sample. You need to determine which locations you want to consider for sampling. Are these sampling locations accessible? Do you have sufficient considerations for health and safety of those who are taking these samples, and so on and so on. We will hear about that later. Another important question is when to sample. It's a time dimension that you need to define. You have to decide if you are sampling at the level of minutes, hours, at the level of day, a week, month, season, or even a year. Again, these will depend on the purpose and objectives of your sampling. The next one is how often you are going to sample. It is about the frequency of taking samples and what kind of sample types you are going to utilize. We will talk later about sample types. Then we come now with lots of practical questions. How? What are the procedures, protocols, methods? We call them SOPs, standard operating procedures. So how you are going to collect samples, how you are going to analyze, how you are going to transfer samples, how you are going to store samples and handle samples. All of that will be covered a little bit later. By whom? Very important question. So you need to identify staff who will do sampling. They have to have sufficient skills and experience to do sampling. And then they need equipment to perform sampling. So what kind of equipment is needed? What kind of equipment is available for sampling? Storage of samples, transport, and also what kind of equipment one needs for health and safety considerations. And then at the end, we take samples in order to be analyzed. So the question is, what kind of analysis you will perform? Because some parameters can be analyzed in several different methods. So you need to decide on which method you want to analyze your sample, which laboratories you will use. Will it be on or off-site or combination on and off-site laboratories? And also what will be the accuracy needed of this analysis to satisfy your purpose of sampling. And last but not least is about data handling. What kind of statistical approaches and methods you will use, how you will interpret the results, what are the results that you are looking at, what are the expected ranges that you would consider as a result of your sampling program or monitoring program. So these are all questions that you need to deal with. Once you have gone through at least one iteration through these questions, you will come up with something called sampling schedule. And the example of that is shown on this slide, where we have taken into account the four of these dimensions that we used here: a time, parameters, locations, frequency, and the sampling type. And that all can be put in a tabular form where we can make a schedule for sampling with all this information. What is important, as I said before, is that you also determine expected range of values of analytical results. In this couple of slides, I have summarized important aspects of the design of a sampling plan. These are kind of checklists that are really useful to consider before you go into the sampling procedures. In these steps, you'll have to define a purpose of sampling, as I mentioned before, a type, scope, and required accuracy of the analysis to be carried out. You need to define the character of the samples to be collected, selection of localities and sources to be sampled, and of the sampling point at these locations, determination of hydraulic and other parameters relating to the subject of sampling program. You need to consider the occupational health and safety and hygiene of those collecting the samples. You need to prepare an optimal sampling program in terms of resources, time, and the budget. But also, you need to cover with your sampling scope the minimum amount of samples that are required to answer your purpose of sampling. Furthermore, you need to select sampling and measuring equipment suited to the source to be sampled and determination of its state. Further on, selection of the most suitable sampling technique in line with the fixed program and selected equipment needs to be given for source or site, including preparations, subsidiary measurements, and observations. When implementing sampling program, the techniques used should comply with a number of general requirements such as reliability, economy, repeatability, and conservation. Selection of appropriate procedures, sample holding, equipment and tools, transfer from site to laboratory, and storage after delivery is also very important. Consideration of the most suitable methods of analysis on site and in the laboratory, the quickest possible interpretation of the analysis, including reliability checks and the possible repetition of the sampling and other factors likely to influence the accuracy of representatives of the analysis, is very important as well. And finally, use of feedback whenever possible to modify a program to an optimal sampling program is really required. Establishment of the conditions necessary for the immediate use of the results and for their storage as primary sources of information in the future, whether for short or long-term use, selection of the appropriate system for data management, selection of the method of documentation to be used throughout the program, and it is also necessary to define the sampling program at early stage in any project. And perhaps the most important thing to remember about any program is that its validity should be kept under continuous review so that it can be changed to meet changing circumstances. Often you are also required to design monitoring program based on sampling. And here I will mention only 6 the most important points. The first one is evaluation of the existing information. The second one is evaluation of information expectations. The third one is establishment of statistical design criteria by aim of statistical software packages. The fourth one is design monitoring network. Fifth, developed operating plans and procedures. And the last one is develop reporting procedures. In summary, a comprehensive sampling plan should include several points: introduction and objectives, the scope, sampling matrix or schedule and sampling sites, methods of sampling, administrative arrangements, health and safety and security provisions, if possible, preliminary site inspection, identification of sampling equipment, containers, preservatives, holding times and shipping, and additional information. On top of that, you need a summary of background information of the site, the issue and purpose of sampling, the breadth of coverage of a sampling plan, investigation methods required to characterize the site, sample types, sampling locations, and field quality control, sampling protocols, personnel requirements, list of standard and non-standard equipment, list of containers needed to be used, methods used to control contaminated materials, including documentation, procedures, solutions to be used, and the storage and disposal obligations. And finally, using the certified laboratory, ensuring the understanding of sample holding times and special training required. And you need to report information sources, sampling media background, sampling protocols and procedures, sampling test and equipment protocols, and laboratory certifications if necessary. Standard methods and operation protocols are very important. They consider physical, chemical, microbiological, biological, and radiological analysis. The samples must be representative, reproducible, defensible, and useful. The analytical methods to be used will be determined by detection limits and the precision required. On the right-hand side of this slide are two most important sources for you. The first one is well known and it exists more than 100 years. It's called Standard Methods for Water and Wastewater Examinations. And it concerns drinking water and wastewater analysis. But when we talk about fecal sludge and septic sludge analysis, the first standard method book, or to be standard method book, is Methods for Fecal Sludge Analysis, issued in 2021. The second one is open access and it's available on this website and you can download it from the discourse website. Sampling methods are mostly divided in two groups: manual sampling and automatic sampling. For manual sampling, you need minimal equipment, it's unduly costly, it is time-consuming, and required skilled technician. When you apply automatic sampling, you can eliminate errors, reduce labor cost, and allow more frequent sampling. There are different types of samples. The most common are grab, or also called spot, random, catch, individual, instantaneous, or snap samples. These are all different names for the same thing. The second one is composite sample, and mostly two groups are known: time proportional and flow proportional. And we have a third group, which are continuous sampling, and are, for example, used for pH measurement, temperature, redox potential, electroconductivity, dissolved oxygen, total organic carbon, phosphorus, nitrogen, chlorine, and some other parameters, and the flow measurements. Let's talk first more about grab samples. Grab sample is a sample collected at a particular time and place and represents only the composition of the source at the time and place. A snapshot. However, when a source is known to be relatively constant in composition over an extended time or over substantial distances in all directions, then the sample may represent a longer time period and or a larger volume than the specific time and place at which it was collected. In such circumstances, a source may be represented adequately by single grab samples. Grab sample involves manual sampling and minimal equipment, but may be unduly costly and time-consuming for routine or large-scale sampling programs. As the name implies, grab samples are simple scoops of the wastewater being sampled and are appropriate where conditions are constant or well mixed and slow to change. Care should always be taken that a grab sample is representative of the whole and should be taken from well-mixed areas on all occasions. Grab samples are applicable when the concentration of a parameter under consideration is not expected to vary significantly with time, when values associated with extreme events are desired, or when the analyte is such that the procedure of composting would destroy the sample integrity. Now let's talk a bit more about composite samples. Composite samples should provide a more representative sampling of heterogeneous matrices in which the concentration of the analytes of interest may vary over short periods of time and/or space. Composite samples can be obtained by collecting multiple grab samples over a period of time, depth, or at many different sampling points. Composite samples are either amalgamated or made up of smaller subsamples and can be prepared in two ways. Automatic samples eliminate human errors in manual sampling, reduce labor cost, provide the means for more frequent sampling, and are used increasingly. The simplest form is a time-related composites, which are collected by using continuous, constant sample pumping or made up of subsamples of equal volume taken at specific time intervals. For example, subsamples every hour composited to make a single daily sample. A composite sample representing a 24-hour period is considered standard for most determinations. Composite samples are applicable when the concentration of the parameter under consideration is expected to vary with time or location. The individual samples that make up the composite may be of equal volume or be proportional to the flow at the time of sampling. Under other circumstances, however, a composite representing a longer time period or a shorter time period may be preferable. The other form is flow proportional composites, collected by continuous pumping at a rate proportional to the flow, by mixing equal volumes of water collected at time intervals that are inversely proportional to the volume of flow, or by mixing volumes of water proportional to the flow collected during or regular time intervals. This later form of sampling is extremely accurate and can be used to establish the total wastewater load. Because of its accuracy, flow proportional composite sample is preferable. Here I provide you a little more information about composite samples. Composite sample may be sequential discrete samples or a single combined sample. 24-hour time discrete sample example is that we use 24 bottles with 4 samples collected every 5 minutes in each bottle. Composite sample is defined by the time interval between aliquots and the volume of each aliquot, T and V. Time proportional sample is the sample where interval time and sample volumes are constant. It is shown in the graph A. Flow proportional sample is when the interval time or sample volume may vary. Option with a constant volume or constant time, depicted in picture B or C. A time composite sample consists of equal volume discrete sample aliquots collected at constant time intervals into one container. A time composite sample can be collected either manually or with an automatic sampler. A flow proportional composite sample can be collected using one of 2 methods. One method consists of collecting a constant sample volume at varying time intervals proportional to the wastewater flow. For the other method, the sample is collected by varying the volume of each individual aliquots proportional to the flow while maintaining a constant time interval between the aliquots. So when we use composite time samples or composite flow proportional samples. Now, if we have a regular fluctuation in pollutant loading over the course of the day and very slight fluctuations in flow, then we recommend the use of composite time proportional sample. However, when we have irregular fluctuations in pollution loading over the course of the day and erratic fluctuations in flow, then our recommendation is to use a composite flow proportional sample. The choice of flow proportional or time composite sampling scheme depends on the permit requirements, variability of the wastewater flow or concentration of pollutants, equipment availability, and sampling location. Composite samples are samples where sampling is performed using calibrated and refrigerated autosamplers, and its preferred method. To ensure representative samples, composite sampling must be performed for no less than 6 hours with no more than 1 hour between discrete samples. These are recommendations. Each discrete sample shall be combined to produce one composite sample. If necessary, laboratory personnel can collect discrete samples by hand for no less than 6 hours with no more than 1 hour between discrete samples. The composite sample container must be cooled during sampling. Now I'll talk a little bit about grab samples versus composite samples. Advantages of composite samples include reduced cost of analyzing a large number of samples, more representative samples of heterogeneous matrices, and larger sample sizes when amounts of test samples are limited. Disadvantages of composite sample include loss of analyte relationship in individual samples, potential dilution of analytes below detection levels, increased potential analytical interferences, and increased possibility of analyte interactions. Use of composite samples may reduce the number of samples analyzed below the required statistical need for specific data quality objectives or project-specific objectives. Sometimes it is more informative to analyze numerous separate samples instead of one composite so that variability, maxima, and minima can be determined. Because of the inherent instability of certain properties and compounds, composite sampling for some analytes is not recommended where quantitative values are desired. For example, alkalinity, nitrate, volatile organic compounds, dissolved oxygen, ozone, temperature, pH, etc. To perform sampling, we need various of devices. Sampling devices should be made from materials that have minimum interaction with and do not contaminate or disturb the sample. They need to be appropriately cleaned between samples. In some cases, it may be necessary to collect the final rinsate for analysis to demonstrate that the sampling device has been sufficiently cleaned to avoid potential errors in results due to cross-contamination. There are several issues with sampling, and I will just mention some. Sample contamination is one of the most important issues. It is related to inappropriate containers or equipment, dirty container caps, containers that have not been properly cleaned, loosely or improperly capped containers, contaminated preservatives, cross-contamination introduced by sampling equipment, exposure to open air which may contain various vapors, and sloppy sampling techniques. Number of samples are determined by sampling objectives, statistical requirements, boundary conditions, and these can be a budget, time, planning, lab capacity, or combination of these. In most cases, it is combination of these. As explained earlier, the number of samples is decided through iterative procedure when you are answering these sampling questions and you design your sampling schedule in which you have to determine the time, the parameters, the frequency and type of sampling, locations, and at the end you will get the total number of samples needed to perform your analysis. Very often you will find out that one of the limitations can be the budget. So you will need to go several times through your iterations to come up to the budget that is acceptable. Sometimes your time dimension is the one which will limit you, which will mean that you will not have enough time to collect all samples that you need because of various reasons, and that the sampling time or sampling period will be really minimized to the minimum amount of samples that you need to get objectives satisfied. Sometimes maybe the budget is not limited or you have enough time, but your lab capacity is not able to manage all the numbers of samples that you will provide. So you need to really to take care about all these different dimensions. There are also limitations in data. There are often missing values, sampling frequencies that change over a period of a record, multiple observation with the sampling period, uncertainty in the sample preservation and measurement procedures, censoring the measuring signals, small sample size, improper data handling, equipment inaccuracies, inadequate data handling, etc. For those who really want to go deeper in this matter, I would really advise to look into this source, the book which is open access, Assessment of Treatment Plant Performance and Water Quality Data, which is also attached to this course, and you can freely download it from the website. Sample volume is important parameter to consider. You need always to collect enough sample volume in the appropriate container in order to comply with sample handling, storage, and preservation requirements. The volume of sample should be sufficient to carry out tests required, preferably not less than 100 milliliters. But this should be calculated. Care should be taken when sampling laboratory experiments. Volume may be limited because if you take too much volume from your experiments, maybe you don't have enough volume to continue your experiments. So it has to be very carefully calculated how much volume you are allowed to take from the experiment, especially if you are working in a lab scale or a pilot scale where the volumes may be limited. Do not use samples from the same container for multiple testing requirements, for example, organic, inorganic, radiological, bacteriological, and microscopic examinations, because methods of collecting and handling are different for each type of test. Sample containers, which are usually glass, polyethylene, polypropylene, or fluoropolymer, are selected according to their lack of interaction with analytical parameters. For example, glass is suitable for samples containing trace organics, as leaching and adsorptions are minimal, but it's not suitable for sampling most trace inorganics because active sites on its surface can be binding inorganic ions. Containers must be clean and may need to be retained and submitted to the laboratory for analysis as a blank. Where reagents are added during the preservation step, a sample of the added reagents must also be submitted to the laboratory for analysis as a reagent blank. In this slide, I show you different types of containers that are regularly used in wastewater sampling, starting from large containers used for sampling larger volumes at the wastewater treatment plants to very small sampling volumes, which are mostly used for laboratory experiments. Sample containers and preservatives are very important in the whole procedure. The appropriate sample collection container and preservative can vary depending on the standard test method used. Therefore, verify a proper container and preservative with the test method being used at the laboratory. To minimize volatilization or biodegradation, keep samples cool but not freezing. Avoid use of dry ice. Preservation method vary between analyses, so you need to closely consult the standard operation practices concerning pH control, chemical addition, use of amber or opaque bottles, refrigerating, filtrating, and freezing samples. This is an example of sample container and preservatives checklist that you can consult and use in your sampling program. But there are more of such information in the literature. It is also important that a temperature indicator bottle shall be included with each shipping container. This is another example of a sampling checklist that you can also consult while you are preparing your samples. You also need to define minimum equipment and tools concerning gloves, safety glasses, disinfection solution, sampling equipment that you will use like sludge judge, dipstick, sample bottle, dipper, vacuum pump, etc., field instruments, chemistry kits, sample bottles with labels and documentation, distilled water, cooler with blue ice, and specific test equipment, for example, IMHO cone, sludge level device, etc. Another important aspect is a chain of custody. Each sample shipment requires a chain of custody log that is maintained from the time of collection during the entire analytical process and until sample disposal. A chain of custody document provides a record of sample transfer from person to person. This document helps to protect the integrity of the sample by ensuring only authorized persons have custody of the sample. the sampling team must maintain physical custody or use custody seal tape on the cool boxes until the samples are handed off to the shipping company or laboratory. You need to have in this process sample labels, sample seals, field logbook, chain of custody record, sample analysis request sheet, sample delivery to the laboratory, receipt of lodging of sample, assignment of sample for analysis, and validity, storage, and disposal of samples. When you are handling and shipping samples, you should use a 24-hour, if possible, overnight delivery service for samples that are shipped to a laboratory. To avoid shipping delays and compromising sample holding times, contact the shipping company prior to sample collection. The shipping company can help determine the appropriate custom arrangements that can be made, if applicable. Samples should be shipped in cool boxes with sufficient insulation and artificial refrigerant, blue ice, or ice contained in double Ziploc bags to maintain a sample temperature of less than 4 degrees for the duration of transportation. Shipping containers that leak fluid, such as melting ice water, will likely be returned to the shipper. Containers should be held upright during shipment, use bubble wrap around individual glass containers, and use adequate packing material to prevent movement during shipment, cushion from shock, and reduce the risk of leakage. The sampler should be responsible for all handling, processing, and custody of the samples, including taking samples to the nearest servicing airport, bus station, or other carrier. The laboratory should be available to receive sample shipments at any time the delivery service is operating, including weekends. If not, check the opening time in advance and arrange a shipment and delivery accordingly. The sample temperature should be measured and recorded immediately upon opening the shipping container and prior to unpacking the samples or removing the packing material. Under no circumstances shall a thermometer or any other device be inserted into a sample bottle for the purpose of determining shipping container temperature. For example, use infrared thermometer instead. Sample holding time depends on nature of sample changes. For example, pH, DO, carbon dioxide, temperature, alkalinity, and other parameters which are sensitive will change. So you have to understand these changes and which parameter can change during this holding and managing samples. Time interval between collection and analysis. For example, there is a different dimension between grub versus composite samples. Because, for example, grub sample is instantaneous sample and can be immediately transferred and preserved. While composite samples, if it's 24-hour composite samples, it can take 24 hours difference between the first composite and the last composite. So during this period, the sample should be cooled to minimize transformation processes taking place in the sample. In general, minimizing the time between sample collection and analysis will provide more reliable and representative analytical data. In this table, you can find the most common wastewater sampling holding time, and you can use it for your reference, but also you will find this information in the SOPs, in standard operating procedures. In the next few slides, I collected some practical do's and don'ts when you are doing sampling. I will also sometimes repeat things that I already mentioned, but it is important to underline some things again and again. Use a clean glass or plastic bottle for samples. Label a bottle, for example, point and kind of sampling, date and time, name of sample collector, parameters of analysis, and so on. Do not touch the inner of the bottle with your fingers because you will contaminate it. Throw the first flash out of pipe away and then take your sample. Stir the sample before you fill it into the flask. Do you need to fill container to the top or not? That depends on the analysis that you want to perform. For example, when the sample is collected, you can leave ample air space in the bottle, then at least 2.5 centimeters, to facilitate mixing by shaking or freezing, unless the analysis requires no head space. In that case, you need to fill the bottle up to the top, because for such analysis, oxygen in the flask let continue a biological processes. For example, the concentration of ammonium will decrease and the concentration of nitrate will increase because of nitrification taking place in the sample, or BOD tests where the oxygen in the headspace will affect the results by the nature of BOD tests. Take care that the volume of samples will be large enough for analysis. Carry the sample as soon as possible to the laboratory or analyze it on site, because biological degradation still takes place. Cool the sample. Do not leave it in the sun. Sample should be stirred, homogenized, or filtrated before you start to analyze. Depends on the kind of parameter for analysis. Check and clean automatically working sampling units frequently. Know what are you sampling, collect information on parameter and basis for analysis, so you can properly collect sample and interpret data. Do not skim surface or drag bottom of wastewater stream. Do not sample dead areas. Do not eat, drink, or smoke when sampling. Control the cooling system, because wrong temperature will change the ingredients. Take care that the whole volume of the connected sample will not be bigger than the volume of the container. Keep sampling bottle closed until it's to be filled. Remove stopper and cap as a unit. Do not contaminate inner surface of stopper or cap and neck of bottle. Fill container without rinsing. Replace stopper or cap immediately and diffuse secure hod around neck of bottle. Collect samples for microbiological examination in non-reactive borosilicate glass or plastic bottles that have been cleansed and rinsed carefully, given a final rinse with deionized or distilled water and sterilized. Collect samples that are representative of the water being tested, flush or disinfect sample ports, and use aseptic techniques to avoid sample contamination. Carefully consider the technique for collecting and representative sample and define it in the sampling plan. Make a record of every sample collected and identify every bottle with a unique sample number, preferably by attaching an appropriately inscribed tag or label. Document sufficient information to provide positive sample identification at a later date, including the unique sample identification number, the name of the sample collector, the date, hour, exact locations, and if possible sample type, for example grab or composite, and any other data that may be needed for correlation, such as water temperature, weather conditions, water level, stream flow, post-collection conditions, etc. Fix sampling points by detailed description in the sampling plan, by maps, or with the aid of stakes, floating markers, or landmarks in a manner that will permit their identification by other persons without reliance on memory or personal guidance. And finally, I would like to mention some hazards related to sampling. There are different hazards: physical, chemical, biological, and weather hazards. Therefore, we need to implement health and safety precautions. Relevant risk assessment and occupational health and safety protocols need to be followed when handling wastes in the field or laboratory. Any personal protective equipment, PPE, required must be used by people having adequate experience and knowledge in their use. Precautions taken and protective equipment and clothing used should be reflected by the associated level of risk. When you are in doubt, assume the worst case outcome will occur. On this slide, I show you the most common used personal protective equipment when you are sampling at wastewater treatment plants. You need to use hat, goggles, gloves, a mask, protective shoes, protective other type of mask, earmuffs, and protective equipment like suits. If you are working in the lab, another type of protective equipment is also used. You need goggles, you need gloves, special shoes, some masks, something for your head and hair, and also lab coat. And something that we should not forget, and it's about sampling of sludges, because so far we were mostly talking about sampling of wastewater at large wastewater treatment plant, at pilot plants, or in the laboratory. However, when we talk about sludges, we are talking about any liquid sludge waste, not to be confused with the wastewater containing low or high amounts of solids. We're talking about anaerobically digested sludge, aerobically digested sludge, dewatered sludge cake, primary sludge, biomass sludge, which is mostly secondary sludge, tertiary sludge or chemical sludge, compost products, dried sludge solid waste, incinerator ash, septic sludge, and fecal sludge. In general, automatic sampling devices, which are widely used for wastewater streams, do not work well with the sludge streams because of the solids content and viscosity of sludges. Therefore, manual composite sampling may be required. For details, please consult SOPs and the sources that I already mentioned. Thank you very much for listening to this lecture.